chat for everyone if they want to download them. And then I think it is a good moment to start. Welcome everybody to this session of the One World Probability Seminar. We have the pleasure to have with us Pierre-Francois Rodriguez and Jiwon Park. So Pierre-Francois will start, and he was a student at ETH with Alan Steedman, and is now an assistant professor at Imperial College London. And he will present this his surprising results on the scaling limit of the two-dimensional discrete Gaussian model at high temperature.
Okay, so thank you, Avelio and Minmin, for the invitation for us to speak here and present our work. And thank you for organizing this seminar. So can you hear me correctly? Yes, and can you also see my mouse moving around? Okay. So, so this is joint work with Roland Bauerschmidt and Jiwon Park, and as I'm sure most of you are familiar with, so this is split into two parts, and I will give the first part, and Jiwon will give the second one. So let me give you a brief outline. So, so basically, I'll introduce this discrete Gaussian model. In fact, I'll introduce two models. I'll introduce also a reference model, which is the Gaussian free field, which you should somehow keep in the back of your mind. Then I'll give you my take on the roughening phase transition for this discrete Gaussian model, and I'll present some known results around this transition. Then I'll introduce scaling limits and I'll actually state our theorem. And I'll give some further remarks and further related works, maybe not so closely related, but still. And finally, I'll give you an overview of the proof, which basically consists of two steps. There is a relatively simple initial step, which we'll do in the first part, and then most of the interesting stuff happens in the second part of the talk. So if you want to see one part of today's lecture, then part two is probably the more interesting one. Okay, so let's introduce the models. So throughout the two talks, actually, we'll exclusively work on the torus, Tn. So this is a two-dimensional discrete torus of side lengths, which I'm going to take to be L to the n for convenience. So it's going to be this kind of geometrically growing scales. And you should think of L as being some fixed large integer, maybe power of 2, but that's a detail. And so, this is somehow a parameter which you can choose suitably large. And then the thing that becomes bigger and bigger, if you take some sort of limit, will be this power n. Okay, so this is convenient for the method which we will apply, and the fact that we have translation invariance is also sort of crucial. Okay, and so then there is a non-negative parameter beta, so this is a positive real number, and there is a fixed point on the torus, which I'm going to call 0. And then, so the measure that I'm going to look at, so I'm going to look at averages of observables f, which depends on n, which is this n and the parameter beta. So this is given by this sort of complicated looking expression. So that's a mouthful. So let's go over it slowly. So you're integrating f, again, some sort of, so there is some density here that looks a little bit Gaussian, and in fact it is. And there is some a priori distribution against this, against which this is integrated for the phi's. So for the special point 0, you're forcing the field to be 0 at that point. So maybe I should say, yeah, phi here is the scalar field. Okay, so it's a random variable which is indexed. It sits on the vertices of your torus, and it has a priori real values. So you can think of this as a surface, if you like. And so at the specific point 0, which is maybe this point here, it's forced to be equal to 0. And otherwise, you have a prescribed a priori distribution lambda here, and you integrate this Gaussian kernel. So this E of phi is the usual Dirichlet energy. Okay, so this is you can write this in several different ways. So if I, maybe the simplest way is you take the inner product of phi with minus Laplacian of phi, where the Laplacian is the usual nearest neighbor Laplacian on the torus. So it's the generator of the simple random walk on the torus. So if you write it like this, then this is evidently a Gaussian density. It's quadratic in phi, and you can almost read off the covariance. Now, another way you can write this is you do a little discrete integration by parts, and then you write it as some multiple of a sum of the gradients. So these are discrete gradients, a sum of phi x minus phi y squared, where x and y range over neighboring vertices. And so here you see that what this measure is really penalizing is large values of the gradients. And in some sense, the gradients are the more intrinsic quantity here, not so much the field itself. Okay, and here, I pinned at a point to make sure that this is well defined and can be renormalized to a probability measure, which is what this prefactor here is doing. Okay, so that's the Dirichlet energy. That's, this is the usual sort of elastic restoring force that you assume if you think that, nearby field values are somehow influenced by some sort of Hooke's law, which is linear in the displacement, and this is the corresponding energy. Okay, so now for the a priori measure, there's two choices that I want you to sort of keep in mind. So the first one would be just to take Lebesgue measure, and then what you get is just the Gaussian free field pinned at the origin. So when I want to talk about this, I'm going to add a superscript GFF to make sure that, to distinguish it. But the actual discrete Gaussian model, which is not really a Gaussian field, but never mind, this is how it's referred to in most of the papers, is when you force these values phi x not to be sort of continuous, but you force them to be integer. And here, for simplicity, I took 2 pi times the integers, because later there's going to be a bunch of cosines, and it's easier like this. But this could be absorbed by suitably renormalizing. So what this is doing is it effectively forces the field values to take on 2 pi times integer values, and so it transformed this integral into effectively an infinite series for every phi x. Okay, and so that's what's called the discrete Gaussian model pinned at 0, which you can think of as this guy conditioned to be 2 pi integer valued. Okay, so that's the model. And then finally, the sort of observables that I want to focus on for this talk, which are in some sense the natural ones, are those which are invariant under shifts. So in the GFF case, it would be any real shift. So phi plus c here means you shift your field configuration at every point by a constant. And of course, that does not affect this Dirichlet energy. And in the case of the discrete Gaussian model, the symmetry would be 2 pi z. So you want this to be invariant under shifts, which are multiple of 2 pi, and of course also integrable. And another way to say this is that these are essentially functions of the discrete gradients, and these are somehow natural observables because they don't really see the fact that you pin at a specific point here. Okay, is there any question about the definition of the model? Anything in the chat? Okay, I'll take that as a no.
Phi plus c is a sum of configurations. Phi plus c. Phi and phi plus c are configurations. Yes.
Yes, that's right.
Why you say that it depends on the gradient of phi?
Because if you have a function which
it is not space translation. It's sum of phi and constant. Yes.
So,
It's not
so what I'm saying
space
here is
translation.
that if you have a function which satisfies this property, then you can write it as a different function, f tilde.
It's periodic function. What is f and is equal to f of phi plus c, but it is not a translation. Yes, it's just in each point. Why it is a
That's
function
right.
of gradient.
Exactly, yes.
Why it's function of gradient.
Yes, and then you can write it as another function of these variables.
Discrete gradient?
Yes.
Why? Let f is why? That's not why.
Well, because you can effectively you can basically go from one point to another by walking along the discrete gradients.
But it is plus constant. Plus constant. It is not a space translation. It's a plus constant in the values of the function of the exploration. Why? How it's connected with gradient?
Okay,
it's not a translation.
I'm not exactly sure I can give you a better answer. So maybe just imagine that, take a specific function. I'm going to take one in a minute. For instance, phi x minus phi y. That's good enough.
No, but it is not phi plus c, because phi plus c, it is not translation. It's phi.
But you see, if you take phi x minus phi y and you shift both by
yes.
a constant, then
okay, it is okay, yes.
That's all I mean to say here.
Okay.
Okay. So, all right. So this this model. So now I'm going to focus on the discrete Gaussian one. Undergoes what's called a roughening phase transition. So let me explain to you what this is. So first of all, if you replace phi by phi over square root of beta, you can sort of rescale and remove the beta from this exponential and put it effectively in this a priori measure. And the way you should read this ratio is really, it's an effective parameter, but the numerator is this 2 pi is essentially the lattice spacing that you have enforced. And the square root of beta is kind of, a parameter which captures the fluctuations, right, of the field. So you have a competition between this gap that you have enforced and the size of fluctuations, of local fluctuations, which is, the variance is proportional to this beta. And so there's two regimes. The first one is when beta is extremely small, then 2 pi over square root of beta is very large. So this gap is jumping from 0 to 1 effectively is very costly. So one way you can intuitively think of this measure in this regime, which is not always a good idea, but you can take this Dirichlet energy. So, you have phi x minus phi y squared up here. You can think of expanding the square, and then the cross term is your usual Ising interaction. And then the quadratic term, you can push those into the a priori measure. And so, you can, all I'm saying is you can think of the GFF as an Ising model integrated against the Gaussian density, which, usually is not necessarily a good way of thinking about the GFF. But here it turns out to be, because if you think of it that way, then in this Gaussian density, well, the next value you pick up, 1 is or 2 pi over square root of beta is very, very far away. So effectively, what this means is that if you force one point to be 0, the ground state would be that everybody is equal to 0, and then occasionally you will see, maybe +1, -1, and maybe +2 or -2. But overall, the interface will effectively be localized, and you can make this precise, for instance, by a Payal's type argument. Maybe I won't go into the details, but the bottom line is that, for instance, if you look at phi x minus phi y squared, so this is a good enough observable for me, then this stays bounded uniformly in n when beta is very small. So this is referred to as the localized regime. So in particular, the variance is small. You can take y equals 0 here. And okay, much more is in fact true. I mean, you know, when beta is small, you could also regularize by adding a little mass to your field, and then, you know, you first take the infinite volume limit, and then you remove the mass, and you will see that as you remove the mass, the sequence of measures is tight, and you end up getting a nice Gibbs measure, a phi Gibbs measure, that is, which has exponentially decaying correlations. Okay, so that's the localized regime. And then there is the other regime, which is perhaps more interesting, which, well, actually both regimes are interesting, which is when beta is very large. And so then, at least intuitively, you might think, well, you know, the lattice spacing now becomes effectively very small. This 2 pi over square root of beta is tiny. So in some sense, the you know, forcing this integer constraint is not really that different than having just a plain Lebesgue measure. And so that's a somewhat slippery slope, because, I mean, this intuition turns out to be true, but it's true in dimension 2, but not in higher dimensions. And the crucial input, which you also need to keep in mind here, is that the sort of background Gaussian field, which is the GFF for this model, is in a dimension at which it delocalizes. And so this is why this sort of heuristic depends crucially on the dimension. And so famously, it was proved by Fröhlich and Spencer at the beginning of the 80s that you know, when beta is sufficiently large, so for instance, if you look at this variance, you have a lower bound, which you know, up to a constant looks like the sort of behavior that you get if this was the GFF. Okay, so now you can ask, well, is this the truth? Yeah, so maybe let me just add one more comment. You know, for these models, you cannot expect to have long range order, which indeed you don't see. And perhaps one good way to see this is to go back and think about the symmetries. So, you know, for this discrete Gaussian model, the symmetry group is in some sense Z. I mean, you have an action by translations which are integers, which is a slightly unusual symmetry. But you know, one way you can think of this is that Z is the Fourier dual of the circle, and in some sense, you know, acting by translations on Z is the same as acting by rotations on the circle. And so, in some sense, you know, the relevant symmetry group which sits in the background of all of this is O2, and so O2 is a continuous symmetry group, and so on very general grounds in dimension 2. So this is called the Mermin-Wagner theorem. You know, any Gibbs measure would have to inherit this invariance, and therefore you cannot see long range order. Okay, so all right. So now, you know, Fröhlich-Spencer was a lower bound. Now you can ask, is this really the truth? And well, and the answer is that it's not far from it. So, so if you take a function, you know, from the torus to the reals, which sums up to 0. So, for instance, you know, if one function would be this, it would correspond to phi x minus phi y. And let's look slightly more generally at moment generating function of this. So, of course, you can, you know, go back and look at the variance by taking you know, maybe 1 or 2 derivatives here. So first of all, at any beta, you have a sort of Gaussian domination bound, which means that this moment generating function is upper bounded by the corresponding one for the GFF. So what this means is that the effect of introducing this integer constraint has the tendency to localize the field. And of course, you've seen, you know, a very dramatic version of this when beta is very small. Okay, so that's an upper bound. And now the lower bound that Fröhlich and Spencer got is something which is you know, almost matching and increasingly so at high temperatures. So when beta becomes very large, this correction that they got in the lower bound goes to 0, and more recently this was quantified further by Garbo and Sepulveda. And I'll get back to this a little bit later. Okay, so good. So that means that this captures somehow essentially what these Gaussian-like fluctuations at GFF-like fluctuations at high beta. But of course, the exact stiffness or the exact order of fluctuations is not completely settled here. I mean, it becomes increasingly better as beta becomes large, but I mean, these are hard bounds, but you could ask if there is some sort of relevant effective stiffness here. Stiffness I'm going to use somewhat simultaneously with this parameter beta. Okay, so here's a little bit of related work, and I'll focus mostly on recent work. So in the high temperature, so high beta, I should say, regime. So there's been a lot of activity recently geared at simplifying arguments to get the existence of delocalized phase. I mean, the work of Fröhlich and Spencer is notoriously difficult, but of course, the upshot is that you get very good results, and also for a bunch of models. So this is something, maybe one noteworthy contribution is by Piet Lammers from a year ago. And then I think there was a presentation at this seminar by a subset of the authors of this paper, so just a few weeks ago. So there's also a paper by Van Engelenburg and Marcin Lies, and there's also one by Lammers and Ott, which actually also settles the dichotomy in some sense of these phases. So there is really a beta C here sitting in between. But I mean, there is a more sort of direct way to see a natural beta C appearing for this specific model, which will become apparent a little bit later. Okay, so this is a high temperature, and then low beta, there's a work on large deviations and entropic repulsion, and also on the extremal behavior, some older and some much more recent. And in fact, right, since I mentioned the extremal behavior, so in the high temperature phase, there's work on the maximum by Matteo Wirth, which is fairly recent, and also this paper contains some results in this direction. And then, of course, if you're there, then there is also a body of work about the extremal behavior of the GFF and logarithmically correlated field, which I think you also heard about very recently in this seminar. So I didn't even start putting all the references here because I could just spend 1 hour talking about that. So this has, been some field of very high activity. Okay, so now about the actual results. So let me explain to you what we did. So this deals with scaling limits in the following sense. So take a function f from ZD to R. Let's assume it's finitely supported and it sums up to 0. And so you can look at these moment generating functions, and you can take a limit as n goes to infinity. And in fact, I mean, this limit exists because it's actually monotone. So for the purpose of this talk, you can just think of this object here as being this limit. So this suggests that there is actually a background measure, and indeed, you can on account of work of Sheffield, this is actually the zero tilt gradient Gibbs measure at stiffness beta for this model, which was shown to exist in his thesis. And it's known to be the unique translation invariant gradient Gibbs measure at zero tilt. But you don't actually need this information for the theorem. You can, if you don't know what that is, you can just think of this quantity as being the limit of this as n goes to infinity. Okay, so now we want to do some sort of scaling limit. So we'll scale as follows. So take a function which is say C infinity, compactly supported on R2, has integrates to 0, so it's in the domain of the inverse of the Laplacian. So for instance, you should think as the gradient of another function with which is regular in some direction, for instance E1, and then for epsilon positive, f epsilon is just the suitable discretization at mesh size epsilon of this function f, which you force to sum up to 0 to mirror this condition. Okay, and so then if you take first just the reference Gaussian free field, then you know that if you let epsilon go to 0, then this quantity here is just going to converge towards the corresponding moment generating function of the continuous Gaussian free field on R2, and this is in a sense a little more than Donsker's invariance principle. Okay, and this is true at any beta positive, and the beta that you see here is also the beta that you see in the limit. Okay, so now here is our theorem, one of our results. So the result says the following: if you take beta sufficiently large, then there exists a function S of beta, which is actually non-negative and exponentially small in beta when beta becomes large, such that if you look at the corresponding moment generating function for the discrete Gaussian model, then as epsilon goes to 0, you converge again towards a Gaussian free field, but the stiffness now suffers a correction, so it's not beta anymore. It's something which is slightly lower, and of course it should be, because as we saw, the effect of discretizing is to localize the field, and so there is a correction which I parameterized in terms of this function S of beta. Okay. So
can you explain what the difference between the last formula and the formulas of previous formula? Looks like the left-hand side looks like the same.
Right. So this is for the Gaussian free field.
For Gaussian field. Okay.
And this is for the discrete Gaussian model.
Thank you. Gaussian.
Okay.
Thank you.
So here are a few more remarks on this. So first of all, we have several related results. So you can go back to the torus, right? So here I first took a sort of an infinite volume limit. If you go back to the torus, so now there is, n is back here, and you can take epsilon n going to 0 as n goes to infinity. So now there's two things we can show. So if you take epsilon n to be L to the minus n, so this means that basically you average over the whole torus. It's a macroscopic scaling limit. Then you get slightly different. I mean, then this boundary condition, this torus, you feel it in the limit, and so you need to replace R2 by the continuous torus over here. Whereas if you do a mesoscopic scaling limit, so you rescale the function, but you're still kind of, your support is much smaller than the macroscopic size of your torus, then you converge to the same thing. So you sort of lose the influence of the boundary conditions. Okay, so these are variations of our results. They're all obtained by similar methods. Now, to illustrate the robustness of this, so in fact, we also have analogous results if you replace the nearest neighbor Dirichlet energy by a range rho Dirichlet energy, which corresponds to jumping, say, uniformly to your neighbors within a distance rho. And maybe the reason why this is noteworthy is that so essentially, analogs of the above hold under this condition. But for instance, so I'm not, the expert here, but I think, the results here of Sheffield, this cluster swapping technique, which gives you the existence a limiting a gradient Gibbs measure, this is difficult to generalize to the case where you have a finite range of dependence. So I'm not sure if that's, this uniqueness of the gradient Gibbs measure is known in this case. I suspect it might not be. Okay, so all right, I want to spend at least a few minutes talking about related results. So, I'm not going to go through all of these references, but at least I wrote them. So if you're interested, you have a place to look. So there is at least 3 sort of different, let's say, areas which have derived results which are in some sense related to this. So the first one is when you replace this Dirichlet energy by some convex function V of the gradient. So, the GFF would be the case where V is just quadratic, and you just integrate against the Lebesgue measure. So then, this goes back to a famous paper of Nadaf and Spencer. Then you can essentially tackle this by probabilistic methods, and you see that, so you have a Gaussian scaling limit, and essentially the effective diffusivity, so the stiffness that you get in the limit, comes from a homogenization problem. And okay, so this has been led to a lot of activity, and notably in some cases people were able to generalize this to the case where V is maybe a perturbation of a convex function. But so to put this in relation to what we're doing, for instance, so we're in some sense at the opposite end of the spectrum, because our function V, if you think of this delta integer constraint as slightly smoothened, then you get some sort of periodic potential. And here you have a definite sign on the second derivative, and the periodic function is kind of the opposite, where the sign changes all the time. So it's a sort of it's the opposite of convexity in some sense. So this is why essentially these techniques are somewhat orthogonal to those that we use. There's also a lot of activity. I mean, this is still area of very active research around properties of the interface and what happens if you have a tilt. So I wrote down some references here, which in particular, there are these surveys which are slightly out of date, but which are maybe a good starting points. This along with Sheffield's thesis, if you're interested in this. Now, the second sort of big area of research is the sort of delocalization results, both quantitative and qualitative, in sort of what I would call combinatorial models. So things like dimers or graph homomorphisms or Lipschitz functions or the 6-vertex model. And here, here's a list of some of the more recent contributions. So for instance, there is the work of Kenyon, which looks at height functions for dimers and their scaling limits to a Gaussian free field. And then there is a sort of third area, which is that of people who are doing sort of a renormalization group, and there are the relevant references I will mention below. Okay, so let me tell you briefly a few open questions which are sort of immediately related to what we did. So first of all, presumably, so you will see this more clearly in the second part. So if I call sigma squared this sort of effective stiffness, then this critical temperature, which I was alluding to, happens when this effective stiffness reaches 2 pi. So this is the same 2 pi or 8 pi that you usually see in the Coulomb gas. And here, I mean, you will see that there will be a leading cosine term, and then there is a point where this cosine term starts to become marginal, and this is sort of a natural barrier, and this is where you expect to find sort of the critical line. And then, you might expect that this function is actually continuous on beta c to infinity, but it could have developed, for instance, sort of an infinite slope as you approach beta c, and so this would be some sort of critical exponent in this. Well, it's not really a critical exponent, but well, this would be a way to witness the phase transition line in this model. But of course, we're still far away from this, because what I stated to you is a theorem which is only valid at high temperatures. So something which is more tangible, and which actually Ji-Woon is actively working on, are asymptotics of say, the variance of phi x minus phi y squared, or even the generating function thereof. So this is not, and when you take a scaling limit, but rather when you're in the infinite volume limit, and you take the distance going to infinity. And so I think we have good things to expect there. And one important corollary, so this would give an expansion that would involve the stiffness parameter S. And if you paid close attention, so in the theorem, our proof actually doesn't preclude the possibility that this stiffness could be trivial. So of course, you don't expect this. You expect the integer constraint to have an effect. But these sort of asymptotics for 2-point functions, which would incidentally correspond to sort of the limiting case here, where epsilon n is of order 1. So if you get the precise asymptotics for that, which will involve S, and you combine this with the results of Garbon and Sepulveda that I mentioned earlier, this would imply that this number S is actually strictly positive. So in some sense, this would settle the non-triviality subtlety in this in our theorem. Okay, so that's that. Then of course there is a zoo of related models, which so for instance, you take a different potentials, not the sort of Hooke's law quadratic potential, but say, for instance, an SOS one, so something like V of X is absolute value of X, and you expect, of course, similar results to be true. But if you start to tinker with this quadratic form, then in practice, this immediately leads to technical issues, which make this a worthwhile project. So this is, this is not at all something which is sort of an easy consequence of what we, that we did, for instance, for this specific example. Another issue is that of dealing with boundary conditions. So as I said, we crucially use the fact that we're on a torus. Otherwise, our method, at least in its current form, doesn't really apply and needs to be extended. And of course, this is, having in mind the possibility, for instance, to find SLEs in the spirit of what Schramm and Sheffield do. So, you could imagine taking, a domain and having two well-chosen boundary values, like a Dobrushin thing, and now you explore some sort of level line in the middle, and you'd like to show that it rescales to some version of an SLE curve. Let me just say this. In what we do, the only way we use two-dimensionality is the fact that the GFF is log correlated. We don't use anything else. So I have good hope that, if the people who are prolific in working on these things might actually find one model in the zoo which maybe has good integrability properties, where you can actually show these things. And let me stress that one nice thing is that you have a whole range of parameters, beta, where you can actually try to find such an SLE. So it's in some sense that that should help. So okay, so this is wishful thinking, I guess, at this point. And another open question, which relates to the regime of small beta, but is certainly also interesting. So it regards, I told you that you expect exponential decay of correlation throughout the phase beta less than BC. beta c, and then as beta tends to beta c, people actually expect that the correlation length, so which is the thing by which you divide in the exponential, will actually not diverge polynomially in the distance to beta c, but rather like a stretched exponential. And so this is somehow what people sometimes call an infinite order phase transition, and so there's certainly interesting physics here, but I think rigorously this is essentially not understood at all. So there's also very interesting stuff to do coming from the left in some sense. Okay, so in the remaining, I guess I maybe have 10 minutes since we started a bit late. I'll give you the overview of the proof, and I'll do the first step. So as I said, there's going to be essentially two steps. Step one is going to happen right now, and step two is going to essentially occupy most of Ji-Woon's talk. So step one consists in smoothing the model and making a sort of sine-Gordon model appear. So what is a sine-Gordon model? A sine-Gordon model is a model where the a priori measure is Lebesgue measure with some sort of cosine term like this. Okay. And how should you think of this? Well, so here, so let me call f of phi this sort of integer constraint that we have for a single spin in the a priori measure. So one way you can think of this, at least intuitively, to model these sort of delta peaks is, you take a cosine, so suitably rescaled so that, its bumps happen at exactly multiples of 2 pi over square root of beta, which I think this is doing. And then, if you send z to infinity, then somehow this potential, which looks like this, will favor these points and favor less the other ones. And it's in a sort of degenerate limit, you get back your sort of delta peaks. Now, this is one way of intuitively thinking about a sine-Gordon model. Now, the drawback of this is that it gives you a sine-Gordon model with an activity variable, which is this parameter z here, which is very large. And the sort of sine-Gordon models that one can hope to understand by means of this renormalization group methods are rather sine-Gordon models where z is extremely small. And so the better thing to do, which is what this step one does, is to actually rewrite the discrete Gaussian model as a slightly different sine-Gordon model. So I put a tilde here. And it's essentially, so this guy will have an activity variable which is much smaller than 1, which is what we want. And basically the high activity is going to be pushed out into high beta. So you can somehow trade z for beta. So right now you don't know what that means, but I'm going to show you this to you in a minute. And then, the second step consists of analyzing this slightly complicated sine-Gordon type model, which now has a small effective activity variable using a renormalization group method, which was largely developed by David Bridges with various co-authors, maybe starting in a paper with Yao. And so I listed here some of the contributions which are most directly related to our work and which have certainly been inspirational. Yeah, so if you paid attention on my first slide there was a little David Bridges sitting in the corner, and certainly he stands out as having spent a considerable part of his career developing these methods. So in a sense, we're walking on his shoulders. Okay, so in the last 5 minutes, let me now explain to you this step in more detail. It's actually relatively straightforward. So what is this sine-Gordon model SG tilde that I was talking about? Okay, so so recall that I call capital F this sort of integer constraint that we put in the a priori measure, and let me refer to E and beta as the expectation for a GFF on the torus. Okay, so this is when you put Lebesgue measure. And now, if I just look for simplicity at this renormalization constant, which is up to a log or something like the free energy, to make it simple. So I take f equals 1, then this partition function is proportional to the expectation with respect to the GFF of the product of these functions. I mean, this is just a sort of a rewrite, I guess. And now the trick, which is not as innocent as it looks, is so you take your free field phi, and you can write this in distribution like another, so a sum of two independent Gaussian fields. So it's a decomposition, and phi tilde is something which is close to phi, and psi is just a field of IID Gaussian random variables with suitably small variance. Okay. And what this does is that this effectively transforms this F into a periodic potential. So let's see this. Right, so if you use this decomposition, then you can write this expectation as an expectation over phi tilde, and then an expectation over psi. And because the psi's are IID, this product here factorizes. So you can pull the product out of this integral. And now you're just dealing with this function f at phi, which you have written as phi tilde x plus psi x. And now you integrate over psi. So what does this do? Well, here you're just integrating, sorry about the noise. You're integrating a Gaussian density, and here you have a bunch of delta functions. So all that's going to happen is that you're going to pick up the Gaussian density of this random variable psi at these values. And this is exactly this sum that you see here, right? This is the density of this psi x at these points over which you're summing this function f. Okay, and I wrote this as E of some log because I want to think of this as a potential. So this function v0 is indeed 2 pi over square root of beta periodic. But the important thing here is, so if you write its Fourier expansion in terms of cosines, what happens? Well, you have to basically up to a constant factor. You have to integrate this against e to the iq phi tilde from 0 to 2 pi. And what happens is that, so you have this extra sum over z. So actually these integrals from 0 to 2 pi or perhaps 2 pi over square root of beta, they sum up to an integral over the whole real line. And then all you're really doing is you're looking at essentially the characteristic function of this random variable psi x, something like e to the I cubed psi x with some sort of prefactor, maybe square root of beta or something. And so of course the characteristic function of a Gaussian, you know it very well, and this is exactly this explicit factor that you get here. And when you take the log of this, so the first term is 1 up to some, I could take out a constant factor here, it doesn't matter, it scales out. And so you'll see that the log of this, which is the potential that I have, actually is of the same similar form. So it has not just one cosine term, it has a whole sum, and they all come with their own activity. So it's actually not just one z tilde, but a whole sequence of them. But their size is extremely well under control, and it decays exponentially in beta, and actually in a Gaussian way in Q as well. And so this, if you plug this back in here, this is this effective Sine-Gordon model that I was talking about. And so in the second part of the talk, Ji-Woon will explain to you how to analyze this model. And perhaps I should just indicate that, soon enough, to make things simple, he will probably assume that, this phi tilde, which is not exactly phi, you can still think of as being essentially a Gaussian free field. And to make things even simpler, you can just think of the leading term here. So just the Q equals 1 term, and then you really, you fall back on your feet where you're looking at sine Gordon model in the usual sense of the world with a small activity variable. And so, just to conclude, I mean, the mystery is still complete at this point because, remember that the statement of the theorem was referring to a correction in the stiffness, and so far this correction has not appeared. So what remains to be understood, among other things, is where this S of beta is coming from, and so this you will see in part 2. Okay, and on these words, thank you for your attention.
Thank you very much. Thank you very much, Pierre. Are there any questions in the chat? Or you can unmute yourself and.
May I ask one question?
Yes, please.
Thank you. It was a great presentation. I would just ask, there was a paper by Biskup and colleagues, and in general, I would be interested if any of this could have relationship also to Liouville measures and LQG. This relates also to extensions to continuum Gaussian free field, but would this make any possibilities also here? Thanks.
Okay, so if you want to start, so I can maybe go back towards the beginning. So of course, there's been a lot of activity in the GFF case of trying to define something which is like the exponential thereof, and I guess what people nowadays call a Gaussian multiplicative chaos. And of course, it's tempting to try to define similar quantities for this discrete Gaussian, at least in the phase where it's rough. Now that we have actually a relatively precise understanding of the scaling limit, this is a natural question. But this is I don't have anything to say about this today. Yeah.
Yes. So Peter asked on the chat whether you can provide information also about about the critical points as well.
So our theorem is for beta large, period. One of the reasons why we also included the range rho case. So, this is similar, like, for instance, the lace expansion and percolation. So, it works up to dimension 11 and not the upper critical one. But if you take a long range version of it, then you can push down the barrier. And here there is something somewhat similar happening, which is that effectively, as you increase the range, you can think of the beta C as kind of receding to infinity. And so at some point, your high temperature regime might actually cover the whole regime up to beta C, and you might be able to get some picture that covers the whole regime up to and including the critical line when rho is sufficiently large. But this again requires significantly more work than what we've done so far. Basically, you have to understand this renormalization group flow with higher precision. So maybe I should mention that one case in which this has been sort of successfully worked out is by Pierluigi Falco. So we certainly were very influenced by what he did. So he looked at the Coulomb gas, which is related. It's basically what you get when you you take this sine Gordon model and you write this cosine as an exponential and you integrate out phi. So he managed to do a second order analysis and describe a piece of the critical curve for the Coulomb gas, which is so of course in his case, again, it's when Z is sufficiently small, because that's sort of what you need to even start with this RG method. But he manages to essentially see a piece of the critical line. So I refer you to his papers for first results in this direction. Yes.
Yes, I had a question. So do you have what happens when you are in a domain instead of just in R2?
So you mean with zero boundary condition?
Yes.
Yeah. So I mean, well, presumably you know what to expect. You converge towards a GFF with zero boundary condition if you take a nice enough domain and you take its discretization. Now, the RG method of David at the level at which it's developed so far requires further amendments to understand boundary conditions. So at the moment, we really use crucially the fact that it's translation invariant and that essentially everything looks the same. Otherwise, near the boundary, different things can happen, and they are not understood by these methods at the moment. Yeah.
Thank you.
So this is really the frontier of this method in some sense, one of the frontiers. Yes.
So, are there any other questions? So if not, let's unmute ourselves to thank Pierre-Francois for his great talk.